Alright, you guys. Today we're starting Unit 10, and Unit 10 is on something called vectors. So vectors are a huge concept in physics, and we use them a little bit in pre-calc just to kind of introduce you to the concept, but if you go on to do more physics-based learning, like in college or whatever, you'll use vectors a lot. So we just kind of scratch the surface on them. But you'll do a lot more in physics. So we're just going to start today with an introduction, kind of what they are, and a couple ways we use them in pre-calc. So starting with what is a vector. So I'm actually going to type this to make it a little bit easier. So a vector is a quantity, so a number, or it's actually a set of numbers, quantity that has direction and magnitude. So that's the big idea with vectors, is that they have both direction and magnitude. They have two features that define them. Typically, we're used to just dealing with one thing at a time. That's called a scalar. So especially like magnitude, like you would measure a desk, like it's 10 inches long. That goes back to magnitude. For our applications, we'll use magnitudes that are things like distance, speed, and force are a couple examples of what we'll see here for our different types of magnitude. Direction is going to be an angle measure. Okay, so looking down here, what do they look like? So a vector, it kind of looks like an arrow drawn at a coordinate point. Okay, so for example, if I have a point here, and I'm starting at the origin, wherever you start your movement, we call that the initial point. So the initial point. And then let's say I travel over 5 and up 6. 2, 3, 4, 5, 6. And I end here. This is called the terminal point. So I'm going to connect those dots. Now the direction matters because we know it has both direction and magnitude. So it matters that you start at the initial point and connect it to the terminal point, and we have to draw an arrow at the end saying we started down here and ended here. So this guy is called the terminal point. Okay, so that's kind of what a vector looks like when graphed. So I can call this vector R, and we use a little symbol to call it a vector. It looks like a half arrow. We'll draw more of these over here in a second. So if I want to label this vector, so this is an image of it, but if I want to write like how to label it, we call it component form. So I would say vector R. So here's my symbol, meaning it's a vector. It's a half arrow on top, equals. So instead of like a coordinate point, see how this is a coordinate point at 5, 6, coordinates are written with parentheses. Vectors are written with these little brackets like this. They kind of look like greater than, less than signs. So its component form would be 5, 6. Okay, and we'll do a ton of things like this. It's written sort of like a coordinate where the component of the vector is your horizontal distance and the vertical distance, the x and the y that you travel to get there. So this distance and then that distance. Okay, so that's how we write a vector here. We also talk about vectors typically in standard position. That would be an example like the one we drew. That just means the initial point is at the origin. Okay, so the initial point of the vector is at the origin. We call that standard position because it makes it easier to draw the vector and do some calculations. Now, you can also have vectors not in standard position, something like this. Or over here. Say it starts here, ends here. So notice they all have an arrow at the end. You don't have to draw these. You can if you want to. These are just different vector examples going in some different directions. We'll look at vectors that are kind of out not in standard position and how to label them, because we have to make sure we know the horizontal and vertical distance, and we'll do all that in a little bit. Okay, so let's look at some other features of our vectors. So the two big features of vectors, magnitude and direction. Okay, if I have some vector v, this is vector v, here's my component form, so these would be replaced with numbers, x and y. I can find the magnitude with an equation. Magnitude is just the length of the vector. It's how long the vector is. Now, when we think about, if I go back up to this picture, if I wanted to know how long this line is, well, you can kind of see how we've created a right triangle right here. So I can pretty quickly use the Pythagorean theorem to figure out the length of this arrow. And that's exactly how we find magnitude of the vector. So the labeling looks like this. If I want to find magnitude of vector v, these brackets here look like absolute value, but they mean magnitude. So they're telling you how long it is. The magnitude of vector v equals the square root of x squared plus y squared. And we'll do some examples in a little bit. If I want to find the direction, that's saying, okay, what is the angle? Thinking back to like our angles from the unit circle, what angle is this guy at up here? I can find the angle using what we know about trig. So if I wanted to find the angle of this vector, I can use tangent because I have information about y and information about x. So I'll do theta, the angle, equals tangent inverse of y divided by x. That's coming straight from SOHCAHTOA, right? Just like we did in the polar unit, finding the angle, we can use our tangent function, okay? A couple things with vectors, though. For us, the direction, the angle, will always be written in one of two ways. So in terms of cardinal directions, we'll do that in a moment, that's like north, east, south, and west. Or you can write it as a positive angle between 0 and 360. This is reference to look back at. We'll practice this in a moment here. Okay. A couple other things, vocab. So we also have distance and displacement. So distance is a term we're more familiar with, and that would be the total length of the path that an object travels, right? So like you're driving somewhere and you want to know the distance, it's the total miles you're going to travel to get there. On the other hand, displacement is really what we're looking at with vectors, and displacement would be the shortest length. Oops, sorry. The shortest length between the object's start and end point, as well as the direction of motion. So that's where a vector comes into play. So for example, like if I'm starting here, this is the start, and I'm ending here. And like, let's say I'm walking a path and I kind of go around, look at some stuff, oh, look at that. This curvy line would be the distance, right? That's the path I actually walked to get there. The displacement would be figuring out, calculating, well, if I could just walk straight there, starting at the beginning, ending here, this would be my displacement. Kind of just like the straight path, quickest way to get there. Okay, so we're really looking at displacement with vectors. All right. Okay, so we also can look at whether vectors are equal, opposite, or parallel. So equal vectors have the same direction, meaning they're pointing the same way, essentially, and they have the same magnitude. What might be different is where they kind of land in space. So the same direction, same magnitude. So if I'm using this picture to list some equal vectors, I can see pretty quickly the vector right here and right here. Just from kind of glancing at them, we'll do calculations eventually, but they look to be about the same magnitude, and they're going the same way. So I can say that vector AB and CD are equal vectors. Okay, so these two guys are equal. Opposite vectors, that just means that they have, they're pointing in opposite directions, but they still have the same magnitude. Okay, so for example, I know that when I look at this picture, it looks like HG is pointing opposite, meaning 180 degrees the other way. So AB and HG would be opposite vectors. Okay, I can also include like CD on this list over here with AB, like these are equal, so they're both opposite to HG. And then lastly, parallel vectors. That just means that they have the same or opposite direction, but in this case, the magnitude doesn't matter, right? Here it's all about the direction. So kind of like parallel lines. So EF is a lot longer, the magnitude is bigger, but it's going the same direction as AB and CD, and it's going opposite HG. So for parallel, AB, CD, EF, and HG are all parallel to each other. Okay, like just like regular lines, like they never cross. They're never going to cross. If I just extended all of them, they're never going to cross each other. KJ, on the other hand, is not parallel, opposite, or equal to anything in this diagram. Okay. Okay, in the next video, we'll look at the rest of these notes. I'm going to stop here because this one's already pretty long. We'll look at how to label the different angles in terms of direction or like from the unit circle, and then we'll start doing a few calculations.